Hello, everyone. We have learned a lot about techniques to solve double and triple integrals, including changes of coordinates and polar coordinates, cylindrical coordinates, spherical coordinates. So, in this video, I just want to do a bunch of exercises to review that material. And I suggest that you stop the video after I read a statement, try it yourself, and then watch my solution. So, let's go. Okay, so in this first problem, this is a true-false question, but let's try to investigate the following. The area of the semicircle center at the origin, radius r, and above the x-axis can be computed using the following double integral. An integral that looks like that, which definitely looks like it is a integral that has been converted to polar coordinates. So let's first see what are they talking about. Maybe we'll write it in Cartesian and then I'll write it in polar coordinates and see if I get the same thing. So now if I write what they are asking me here, x and y coordinates, we're going to be above the x-axis, and it's the area of the semicircle center at the origin, radius r. So if I put here r and I put here r, then I can draw the entire circle, more or less a circle. And we are talking about the semicircle above the x-axis. So we are really talking about this region that is above the x-axis, which is the semicircle. Great. So here in x, this is minus r. It goes from minus r to r. So if I was going to express this in Cartesian coordinates, I'm going to need also to know what is this equation right here. The equation of a circle is x squared plus y squared equals the radius squared. So that graph, the top of the graph, will be, if I solve for y, I will get r squared minus x squared square root with a positive, while the bottom of the graph is the one that I get with minus the square root of r squared minus x squared. So if I was going to compute the area in Cartesian coordinates, that would be the integral from minus r to r, integral from minus the square root of r squared minus x squared to the square root of r squared minus x squared of 1 dy dx. Okay, and now if I'm going to convert this to to polar coordinates, that same region, this region that is that semicircle r, the region r in polar coordinates would be, it would be r's and thetas, such that, first of all, the radius can go from 0 to r, because let me do it perhaps in purple. I can go in one given angle. The radius can go from here all the way up to here, and that length of a radius is r, the largest it can be. So the radius can be going from 0 all the way to r, while the angle for this, as drawn, from here to here, the angle is from 0 to pi. Okay, so I would say that theta goes from 0 to pi, and that is the region r. And therefore, if I want to convert that integral, the integral of 1, the area of r, and I want to express it in polar coordinates, I would express it as the integral, first of all, in angle from 0 to pi, then in radius from minus 2 to, from 0 to r, and then of the function 1 times my conversion factor. Remember that that is r dr d theta. And you can see that this does not agree with this. And what is happening here is that this region that is being described is this semicircle, is the circle that is going with angles from pi over 2 to minus pi over 2. So this region that is being described by uh, this integral is this semicircle. However, that semicircle and the semicircle we are talking about have exactly the same area. So my answer here is going to be true because they have the same area. So if they're asking me, is this integral giving me the area of a semicircle like this, the area of that semicircle is the same as the area of this semicircle. So that is true. If they were asking me, is this region really describing this semicircle? The answer would be no, because it is describing the semicircle north of the x-axis instead of the semicircle east of the y-axis. So that would be my answer, and this would be the representation, the closest representation to the region that they are talking about would be this one, and not the one given. But again, the one given, it is also given the area of a semicircle, and any of the semicircles have the same area. So all in all, I would actually write in the page that yes, the area is true, that integral, it is truly the area of the semicircle they're asking. It is true, the area can be computed. It can be computed with that integral, but I would write, but the area described, the region described, is the wrong semicircle. Okay. And that can have consequences. Here we're just integrating the area, but if we were going to integrate a function, then the values of the function could be different in this region that they would be in this region over here. So you'd really have to, in the bounds of the integral, when you're integrating a function that is not just the function one, you really have to be careful and integrate over the region that is really the region that it's intended to be integrated over. Okay, so let's see another example. In this example, they are asking me, again in a true-false way, they're asking me the following iterator integrals describe the volume of the same region E. Both integrals are triple integrals. They're both integrating the function 1, so they are calculating the volume of whatever region these two integrals describe. So what we're going to do is I'm going to call this region A, and this region here B, and we're going to try to figure out what regions are being described. So first of all, let's interpret the region A. The region A is telling me that x is going between -1 and 1. The region is telling me that y is going between x squared and 1, and that z is going between 0 and 1 minus y. Let me just try to sketch what that looks like in case it helps when I compare it to the other one. So here is x, here is y, and x is going from 1 to -1, and y is going between two graphs. The graph of x squared, y equals x squared, is a parabola like so that actually goes by 1, 1. So, and y equals 1 is this line here. So this is y equals 1, and this is y equals x squared. So the region they are asking me, or the projection of the region to the xy plane, is given by this part of the inside of the parabola. All right. And then the z coordinate is going between 0 and 1 minus y. So let me try to sketch that in 3D. Here is x, y, and z. So let me first sketch this region we just found out on the xy plane. Is going to be a region like this, where this is the 1 in y, and here in x it goes between 1 and -1. And what are the limits for z? They're going between 0, so it is going to go from the xy plane up to something else. This new something else is z equals 1 minus y, which is, if I put it, this is the equation of a plane. And if I put it in scalar form, this is y plus z equals 1. which is a plane that goes, for example, by the points 0, 1, 0, or by the points 0, 0, 1, or in fact, the x can be anything in those. So I have, for example, every x, 1, 0 is in that plane. The normal vector, if that helps, is the vector 0, 1, 1. And that is a lot of information for me to say that the plane contains this entire line. It goes through that point, which is 0, 0, 1. So it is this plane right here. Okay. And the z coordinates have to go from the xy plane all the way up to this plane. So the top is going to look like this. And then what we're going to have is some sort of like wedge. So the region A looks something like this. Okay, so it's like a circular wedge. Okay, so let's now investigate the region B. B is given by the outermost integral is in x, so the first bound is given is it's giving me is that x is between -1 and 1, like in region A, so that looks good. And then it's telling me that z is between 0 and 1 minus x squared, and that y is between x squared and 1 minus z. So if I just try to sketch that also, what it's telling me is that first I'm going to describe something in the xz plane. So in the x z plane, I'm again in x going between 1 and -1, so this whole thing. And z is going between 0 and 1 minus x squared. 1 minus x squared is a parabola, but is a parabola that opens down. So it is a parabola like this. And the region then is going to be this region. So let me sketch that in 3D. Here is x, y, and z, and now the region is going from 1 to -1 in x and in the x z plane, like so. That's the projection to the xz plane. But then y is going from y equals x squared up to y equals 1 minus z. So what are those bounds? Y equals x squared is the parabola that we had before, and y is equal to 1 minus z is again z plus y equals 1, which is the same plane. So the y is also going to go, if I draw the plane before, the y is going to go between this sort of like this is a cylinder, a cylinder. It's a parabolical cylinder like this, and it's going to go between the parabolical cylinder and the plane given like before. So all in all, if you follow sort of like that sketch, the region that we're getting is exactly like before. It is going to look like a wedge like this. So we're actually getting the same wedge. Let me try to figure out, just by looking at the both descriptions, that it is in fact the same region. Right. So again, the region A is given by -1 up to x up to 1. Then y is between x squared and 1, and z is between 0 and 1 minus y, while the region B was given by -1 up to x up to 1, z between 0 and 1 minus x squared, and then y is given between x squared and 1 minus z. So notice that the last equation, it's telling me that y is going between x squared and 1 minus z, but z is between 1 between 0 and 1 minus x squared, the largest z can be is when x is 0. So z is going at most up to 1. And it is also telling me that, well, the smallest z can be is 0. So this is at most up to 1. So this tells me that the y coordinate is also going between x squared and 1, which is what we had here as well. And what about the z coordinate in terms of y? We have, first of all, that y is less or equal to 1 minus z. And this tells me that z is less or equal to 1 minus y, which is this part of that inequality. And on the other hand, we do know that z is bigger or equal to 0 because we know it from this. So we also have that z is between 0 and 1 minus y. So if I put it all together, I have first this one. It tells me that for b, I can also define it as minus 1 to 1. Oh, that we had it here that y is between x squared and 1, and that z is between 0 and 1 minus y, which is precisely the same thing we had here. So both regions are precisely the same thing, and my answer is yes. It is true that both integrals are actually describing exactly the same integral over the same region, and they're computing the same volume of the same region, which was that circular wedge. Let's see a different problem. Here they're asking us to evaluate the following statement. The intersection of the surfaces given by phi is equal to pi over 4 and rho equals to 2 is a circle of radius 2. Here we are using, they're using spherical coordinates to describe two surfaces. And remember that in spherical coordinates, we have coordinates rho, theta, and phi. And they are fixing two surfaces, one that says that rho equals 2, and one that says phi is equal to pi over 4. Now, rho is equal to 2 is a sphere of radius 2 because it's precisely all the points away from the origin at distance 2. But pi over 4, phi is equal to pi over 4 is what object? If I go from the x-axis, if I go pi over 4 from the x-axis, then every point that is at pi over 4 from the x-axis is on that surface. So that is a cone. So this is a cone, while this is a sphere of radius 2. So we are intersecting a cone and a sphere of radius 2. So let me draw that over here, that I have, let's just draw the semisphere like this, and then I have the cone, and the intersection over here is going to be a circle, but the question is whether that is of radius 2. And I don't think it can be, because this distance from here to here has to be 2. So whatever this radius is, it is not going to be 2. Why? This over here, this shape over here is a triangle. This radius is 2. This is the radius I'm trying to figure out. This is 45, so pi divided by 4. So the sine of pi divided by 4 will be r divided by 2. The sine of pi over 4 is the square root of 2 divided by 2. And that tells me that the radius is a square root of 2, which is not 2. So the cross section is a circle. So it is, yes, it is a circle, but of radius a square root of 2 and not 2 like they say. So the statement as written is false. Okay, next problem. So in this problem, they're giving me a region and they want me to write an integral that represents the volume of the region in two of the three coordinate systems that that we have studied: Cartesian, cylindrical, and spherical. So let's try to understand the region before we decide which ones make the most sense. So the region is the following. Here is my triple coordinates. It has to be above the xy plane, so it has to be above the xy plane, and it has to be below z equals a square root of x squared plus y squared. Remember that that is the equation of a cone, and it has to be inside x squared plus y squared equals 9, which is the equation of a cylinder, and that cylinder has radius 3. Okay, so all in all, what I have is that it has to be this region here and inside, above the xy plane and below that cone. So it is a region like this in space. Okay, so it goes like this. So I'm looking for a cylinder that is missing a cone. Okay, and I want to find the volume of that thing. I can certainly do Cartesian coordinates for this. And better off, if I'm actually going to compute this volume, I would prefer cylindrical coordinates for sure. Spherical coordinates, I do not think is a good idea because there is no spherical symmetry. There is definitely a symmetry above the z-axis. It's symmetric above the z-axis, but to be symmetric with respect to the origin, the radii would have to be, at least in this region, have to be the same. So if instead of a cylinder I had a sphere and cut out a cone, that would be that would have some spherical symmetries. But as it is, because it is a cylinder instead of a sphere, I have cylindrical symmetries but not spherical symmetries. So first I'm going to do this in Cartesian coordinates. So to solve this in Cartesian coordinates, to express the volume in Cartesian coordinates, first I'm going to draw the projection on the xy axis. And remember that the projection on the xy axis is a circle of radius 3 because it's given by x squared plus y squared equals 9. That will be the projection in the xy plane. So this is 3 and minus 3 and minus 3 and 3. So what I can do is set this up as type 1 integral. So I'm going to start with x. So the region is going to start with x between minus 3 and 3. The top now for y, so x is going from here to here. For a given x is going to go, or y is going to go from here to here. So y is going to go from, if I solve for y in the equation of the circle, that is the square root of 9 minus x squared, and the bottom graph in terms of x is minus the square root of 9 minus x squared. So y is going between minus the square root of 9 minus x squared and the square root of 9 minus x squared. And finally, z is going from the xy plane, so z equals 0, up to the square root of x squared plus y squared. So all in all, if I want to set this up as a triple integral, I would go in x between minus 3 and 3. In y, we're going to go from minus the square root of 9 minus x squared to the square root of 9 minus x squared. In z is going to go from 0 to the square root of x squared plus y squared in z. And I'm integrating the function 1 because I'm integrating a volume. So that is the expression that I was looking for in Cartesian coordinates is given like this. Now I'm going to express the same integral, but in cylindrical coordinates. In cylindrical coordinates, that object that region in cylindrical coordinates is as follows. First of all, in the xy plane is where I'm going to use polar coordinates. So the radius was going, the region in, let me show you, the region that I'm talking about is this region in the xy plane is a circle of radius 3. So the radius is going from 0 to 3. And the angle, because it's the full circle, the angle is going between 0 and 2 pi. The z coordinate, though, is going from 0 to the square root of x squared plus y squared, which I have to convert to radius and theta, but I know that r squared is x squared plus y squared. So if I substitute r squared inside the square root, I'm just going to get r, because the square root of r squared is just r. So all in all, I have those equations. So I can now describe the integral of E dv in cylindrical coordinates as the angle going from 0 to 2 pi, the radius going from 0 to 3, the z value going from 0 up to r, and the function, I'm integrating the function 1. It doesn't need to be converted any farther, but I do have to multiply by the conversion factor. So I have to multiply by r. So this is the integral we were looking for to convert the volume integral in cylindrical coordinates. That's the integral we would have to solve. Okay, here's a new problem. In this problem, first they're going to ask me to sketch a region D, which is bounded by these two curves, and then we'll probably do an integral over that region. So let me sketch that region first. So here is x and y, and the first curve is y equals x squared, which we know very well that is a parabola that looks like this. So I'm going to label it. And now I have to figure out what is the graph of x is an eighth of y squared. That is a parabola in this direction, right? And we now have to figure out what we have to figure out now is where do they intersect. So if I put, say, x is 1/8 y squared, but I know that y is equal to x squared, so I'm going to intersect this with y equals x squared just to see what the points of intersection are. Then y would be x squared, so I get that x is an eighth of x to the fourth. So 1/8 of x to the fourth minus x would be 0. And that tells me if I take a common factor of x, that would give me an eighth of x cubed minus 1 is 0. And that gives me 2 points of intersection when x is 0, or when an eighth of x cubed minus 1 is 0, which gives me that an eighth of x cubed is equal to 1, that x cubed is equal to 8, and therefore x equals to 2. So this gives me 2 points of intersection at 0 and when x is 2 right here. So this is the graph of x is an eighth of y squared, and the region we are going to be integrating over is this region. This region right here is the region D we're looking for. And now we want to write a double integral that represents the area of the region D in the order dy dx. So they mean go first in x and then in y. Remember that the region we just found out looked like this. It was going up to x equals to 2. Let me just remind you what the region looked like. So we have y equals x squared like this, and we have the other one, which is x is 1 over 8y squared, which is, by the way, y is equal to the square root of 8x. And this is the region we're integrating over. So the region can be described, the region D can be described as x going between 0 and 2, and y is going from here to here. So from x squared all the way to the square root of 8x. So the integral that we're looking for, the integral of the region D1, the area, in Cartesian coordinates, will be the integral from 0 to 2 in dx, and the integral from x squared to the square root of 8x dy, and just the integral of 1 because we're integrating area. So this is the integral we're looking for in this part of the problem. This is the integral we are going to have to solve. But actually, before we do that, they're asking me to write a double integral that represents the area of the region D, now in the order dx dy. So now remember again that we have a region. It was going from 0 to 2 in x, and then the graphs were this one, y equals x squared, and then the other one up to here was x is an eighth of y squared. Now, what is this point right here? When I write x equals 2, sorry, this was y equals x squared. So this point right here has to be 4. X is 2, so y is 4. So the y is moving between 0 and 4, and between two functions, and the x then will go from here to here, moving between this function and this function as functions of y. As functions of y, this one is x is the square root of y. So in the order of integration, I can also integrate this region D, 1 dA, as going first in y between 0 and 4 dy, and then dx is going to go, x is going to go from uh, below we have an eighth of y squared, and above is the square root of y of 1, of the integral of the function 1, because we're finding in an area. So in that order of integration, the integral looks like this. And actually, there is no part D to this problem to actually evaluate these integrals, but I suggested you try that you evaluate this integral and get a number, and then that you evaluate the other integral in the other order we found and find hopefully the same number, and both represent the area of this region. So do that. Find those two, the values of those two integrals, and compare them and make sure they are the same. Instead, we're going to move on to a new problem. And in this problem, first they're asking me to rewrite this integral in polar coordinates and then evaluate it. So let's start with the rewriting part. What region are they asking me to integrate over? The x coordinate is going from 2 to minus 2. And the y coordinate is going from 0 to the square root of 4 minus x squared. I know that that is a semicircle because y equals the square root of 4 minus x squared. If I square both sides, I get y squared is 4 minus x squared, which is equivalent to x squared plus y squared equals 4. So it's a circle of radius 2. So the region I'm integrating over is this region. So, and then the function x squared plus y squared to the 3 halves is, in terms of r and theta, this is going to be r squared to the 3 halves, which is just r cubed. So all in all, what we get is that the integral, if this was I, in polar coordinates, I is, it goes in theta. You see, theta is only going from 0 to pi. It's not going to the full circle. So in theta, I'm going to write an integral from 0 to pi. In radius, the radius is easy. It's just going from radius 0 to radius 2. The function that I'm integrating is r cubed. And I have to multiply by the integration factor, which is r. In this case, dr d theta. So all in all, the first part of the problem, which is rewrite it in terms of polar coordinates, I get the integral from 0 to pi, the integral from 0 to 2 of r to the 4 dr d theta, which is going to be pretty easy to integrate. Okay, so now we have to integrate the integral from 0 to pi, from 0 to 2 of r to the 4 dr d theta, which will be the integral from 0 to pi of r to the 5 divided by 5 between 0 and 2 d theta, which is the integral from 0 to pi of 2 to the 5, which is 32, divided by 5 d theta. That is a constant that can come outside, 32 divided by 5, and then integrate from 0 to pi d theta. That will be 32 divided by 5 of theta between 0 and pi. And at pi, I get pi. At 0, I get 0. So this is 32 pi. So this is 32 pi divided by 5, and that is the value of the integral we were trying to compute. And I think this is a lot easier to do in polar coordinates than it would be to try to do it directly in Cartesian coordinates. In the last problem that I want to do in this video, we're going to set up an integral for a volume of a region that is described as follows: is above the xy plane, below the cone pi over 6 for phi, and inside the sphere of radius 2. So let's see what that means. So first of all, that cone, to draw that cone, I have to go pi over 6 from the z axis, and then draw the cone like that over there. And now it has to be below that cone, but also, so it has to be below the cone and inside the sphere. So if I now draw the sphere above the xy plane, then it has to be something like this. So all in all, what I get is some sort of sphere where I have actually removed a cone from the inside of the sphere. Okay, so it's going to look something like that. So first of all, what is that region E then in coordinates? The region will be, first of all, you can see that the radius or the distance from the origin can go anywhere from 0 to the sphere itself, which is of radius 2. Here's the equation of the sphere, and that 2 squared tells me that the radius of the sphere is 2. So in spherical coordinates, these will be rho, phi, rho, theta, phi, such that rho can go anywhere between 0 and 2 within the sphere. Theta, you can see that there is no restriction around the z-axis. There is no restriction to what angles I can be in the xy plane. The angles are all of them from 0 to 2 pi. And it is phi that is restricted because I can't go inside the cone. So you see that the cone spans from 0 to pi over 6. I can go from pi over 6 in angle all the way to the xy plane, which would be pi over 2. So that tells me that the angle phi is restricted between pi over 6 and pi over 2. And that precisely describes the region I'm trying to integrate. So the volume integral over E of 1 dV will be given by, in phi, is the integral from pi over 6 to pi over 2. In theta is the integral from 0 to 2 pi. In radius is the integral from 0 to 2 d rho. And then I have to integrate the function 1, and I have to multiply by the conversion factor to a spherical, which is rho squared times sine of phi. So that all in all, this is the integral that we would have to compute to compute the volume of that region.